So, we have been discussing different type of potentials and the solution of Schrodinger equation in those kind of potentials. So, let us finish some 1D, some more 1D problems, and let us start with a delta function potential. So, delta function potential, as we shall see, that it has slightly different boundary conditions, but nevertheless it is a tractable problem. Then we shall do linear harmonic oscillator, and then we will go over to more than one dimension, that is problems in 3 dimension, and we will talk about Schrodinger equation, solution of Schrodinger equation in 3 dimension. And in particular, we shall talk about hydrogen atom and the solution of the Schrodinger equation in hydrogen atom, finding its stationary states and the bound state energies, etc. And then we will talk about angular momentum and the commutation relations. We will keep this discussion short, and rigorous derivations will not be given, but the main results and the implications and how to analyze the main results will be discussed. So, let us talk about an attractive delta function potential, and it is attractive. You see that it is in this minus a into v naught x. So, that is the form of v of x. So, there is a delta function which is like a sharp peak at x equal to 0. This 0 in the blue color, it shows that it is at x equal to 0, and this is the x axis shown by this arrow. And then we have energy, which is energy of the particle is negative. So, and that is shown by this green dashed color. And now, what it is saying is the following, that the solutions of this problem are written as this is say region 1 and this is region 2. And we have this the solutions are written in region 1, which is x less than 0, that is this region, and this is x greater than 0. And the solutions are as follows, that at x less than 0 it is equal to a exponential this kappa x, and for x greater than 0 it is a exponential minus kappa x, where kappa is given by this all these root over of minus 2 me by h cross square. Of course, E is the mod E here that is used. Psi is continuous, but d psi dx is not continuous. Pardon me, the part of it actually went to the next line. So, this psi is continuous, but so at x equal to 0, the psi is continuous, but the d psi dx, even if it is not continuous, it is discontinuous by a known amount. And what we do here is the following, we use minus h square by 2m d2 psi dx2 and a minus a v naught delta x psi, and psi of x is equal to E psi of x. And what we do is that we integrate this equation, and that gives us this minus h square over 2m d dx of d psi dx. So, if you integrate this, it becomes d psi dx. This is at x equal to some plus epsilon minus x equal to d psi dx evaluated at x equal to minus epsilon, and this is what is written there. Now, we use this relation for the delta function. So, delta of x psi of x integrated from minus infinity to plus infinity gives you and integrated over all x gives you psi of 0. And so, this is so psi at 0 is continuous. So, we can use this, and so this thing becomes equal to minus 2 ma v 0 by h cross square, and the right hand side, which is E psi x dx integrated from minus infinity to plus infinity, gives us 0. because you actually calculate this is equal to psi at epsilon minus psi at minus epsilon. It became a little messy, but I hope you understand that the right hand side does not give any contribution. So, the only contribution to this d psi dx in just the left of the barrier and just the right of the barrier is given by 2 ma v naught by h cross square psi at 0. And when you calculate this d psi dx from these expressions or from the solutions of psi of x, you get minus kappa and minus kappa. So, that minus 2 kappa is equal to minus 2 ma v naught by h cross square. So, kappa becomes equal to ma v naught by h cross square. That gives the bound state energies and or these things to be minus m a naught square a square v naught square by 2 h cross square. And you can easily calculate the this normalization by doing this so this is for, so if you take this psi mod square x integrate it over all x, for if you take it minus infinity to plus infinity, you have to really break it up into minus infinity to minus epsilon and use the first solution which is there for, so it's a square e to the power 2 kappa x and plus epsilon to infinity again a square into e to the power minus 2 k 2 kappa x, and that's equal to 1. And from there you can calculate a square and then put it back, and this problem can be solved. Now you know the eigenfunctions and the eigenvalues of this equation or of this problem, which is an attractive delta function. Similarly, a repulsive delta function can also be solved. We will probably see that in an assignment problem. So, let us look at simple harmonic oscillator. You have encountered oscillators in different branches in physics, and you have looked at a classical oscillator, and most commonly you have looked at a pendulum which is hung from a rigid support. So, there is a string of length L which ties a bob of mass m, and then for small oscillations you have calculated the time period, and this equation of motion for this case is a simple harmonic motion. You have also looked at a mass spring system where the spring is attached to the left end with a rigid support, and then it is tied to the right end with a mass of m, and then you have applied a force and which displaces it from its equilibrium position by say some amount which is say given by x, and you have written down the equation of motion which is nothing but f mx double dot equal to minus kx, and where k is called as a force constant or the spring constant, which is a property of the spring. And so, this is your f is equal to minus kx, and which is k is nothing but minus m omega square, and that gives you the solution x of t equal to x of 0 cos omega t plus v 0 divided by omega sin omega t, where omega is given by the time period, which is in terms of the time period as 2 pi over t. And the force that is can be written as a negative gradient of a potential. There is a conservative force. So, the potential corresponding to this is half m omega square x square, which is a simple parabola. Okay. And you are very familiar with this, so I am skipping all of that. And now energy is of course a constant of motion, which is kinetic energy plus potential energy. So, as the displacement happens, so once you pull this mass towards the right and then leave it, so it will go back because of the restoring force. This is called as a restoring force, and the negative sign says that it will go in the original direction, or rather the direction from which it has been displaced, and it will press the spring towards the left, and then it will again cross the equilibrium position and will come to the right. And if you neglect friction completely, then the mass will keep executing the simple harmonic motion. And while it does, we can calculate the kinetic energy, and the kinetic energy is as displacement, it will have the maximum kinetic energy at displacement equal to 0, where you actually pull this spring or the mass, and then as it goes to the extreme, the amplitude of the displacement, that is the maximum displacement, the kinetic energy will go to 0, and then because the mass will stop momentarily, and then it will again go towards the equilibrium position and overshoot the equilibrium position on the left, and this motion will keep going on, and the potential energy will show a parabolic increase with this displacement. This capital A is the maximum displacement, and it is on both sides, it is plus A and minus A, and the potential energy will undergo a sort of parabolic fashion. It will increase in a parabolic fashion, will reach the maximum when the kinetic energy goes to 0, and at each point, if you add both the graphs, you will get the total energy, which is shown by this violet line. So, this blue line, if you take a point here and take a point here, you get a point here, and even if you take a point here and a point here, you still get a point here. So, which is a constant energy, and this system is known to have constant energy. So, coming to the solution of this is the x of t, or the displacement as a function of t, will depend upon two. So, because it is a second order linear differential equation, there are two unknowns. We have sorted out these unknowns here by this is the amplitude of the cosine omega t term, which is equal to nothing but equal to the displacement at t equal to 0. And the second one, that is a sine omega t, which will involve, the coefficient will involve a velocity at time t equal to 0, and so it is v 0 by omega, and the particle will execute this oscillation. Let us go to this quantum mechanical oscillator, and we now show this parabola that we talked about. And if you expand the v of x about x equal to 0 by a Taylor expansion, so then it becomes a v at x equal to 0 plus a del v del x at x equal to, evaluated at x equal to 0, and x minus x 0, and x 0 is equal to 0 here, of course. So, and plus half of del 2 v del x 2, evaluated again at x equal to 0, x minus x 0 whole square, plus all the other terms. This term is a constant. Okay, so this term is a constant, so you can actually remove it from the potential energy, because a constant term will simply shift the energy up or down. It does not have any x dependence, but the one that has x dependence are these two terms, but this term is equal to 0, and the reason it is equal to 0 is that del v del x is nothing but the force. So, if there is no force acting on the system, then at equilibrium this force will go to 0, and you do not need to consider the first term, or rather the second term as well. So, the only non-zero term and relevant term is this third term, which can be written as half k x square. I said x not equal to 0 here, so that is why we have not put x naught, and this k, which is, as I told, it is called as a force constant or spring constant, can be written in terms of the mass of the oscillator, that is the particle which is executing the oscillation, and in terms of mass and the angular frequency, which is equal to half, which is equal to m omega square. So, half m omega square x square is the potential that the particle will feel in this kind of a potential well. So, it is a harmonic potential well, and the particle cannot escape, and so that means that the energies or the eigenstates will be like the bound states, and we will have to calculate the energy, the quantization of energy inside the well. And now, in the sense that this energies are called as a quantized oscillator energies, and they will have something which is very subtle. It will be different in a subtle way from the energy levels that you see seen in this particle in a box. Okay. So, we will have to calculate the energy and the wave function, and what are the properties of the wave function. The wave function should be continuous and d psi dx is continuous, unlike the delta function case. Here both psi and d psi dx be continuous because there is no infinite discontinuity at any point. So, this potential is smooth, which looks as half m omega square x square. It exists at any value of x and remains finite all throughout. So, Vx it becomes infinity as x becomes infinity. So, the particle cannot escape to infinity at any finite energy, and we can understand it that if V becomes infinity, psi has to become 0 in order for the second term. I apologize for not writing the psi here, there should be a psi there. So, the second term demands that the wave function has to vanish at x equal to infinity. Okay. So, the particle cannot escape to regions where x is very large or infinitely large, and the solutions are bound states that should decay as psi goes to 0 as mod of x on either side of x. Why we are writing mod of x is that this potential has an inversion symmetry. So, there is any point here has a corresponding point at minus x. Okay. So, that is why we are writing a mod of x, and these bound state energies, as we shall see, that they will come out as discrete energies. Okay, there are some technicalities, but mostly I sort of do not talk much about it, but I will only discuss the important results. Nevertheless, some mathematics will have to be there. So, what we do is that we make a variable transformation from x to y, where we write y equal to x root over of m omega by h cross, and E is equal to h cross by 2 and this epsilon. So, we introduce this epsilon to be the new energy scale, which is dimensionless energy. And then if you do that and write psi in terms of y instead of x, it takes a form that minus h cross omega by 2, psi double dash that you see here means that d2 psi dy2, we have dy2. We have changed the variable from x to y. So, whenever you need to take a derivative, what you should do is that your d psi dy is equal to d psi dx and dx dy. Okay. So, dx dy can be calculated from the transformation that you have used for relating y and x, and after that this equation, Schrodinger equation, takes this form which you see here, and you can cancel h cross omega by 2 from everywhere because it is not equal to 0. So, you get an equation which is psi double dash y plus y square psi of y equal to epsilon psi y. And if you further introduce this new variable f of y instead of psi of y, but by just scaling it with a Gaussian term which is exponential minus y square by 2, you get an equation which is minus f double dash which means d2f dy2 and minus 2y f prime or f dash plus f is equal to epsilon f, and this becomes your new form of the Schrodinger equation that you need to solve. And we do not go into solutions, the rigorous solutions of that, but then it can be figured out that if epsilon does not have this quantization, then this f of y, that you see here, okay. So, this f of y will grow rapidly as y going to infinity. So, that in fact it grows as exponential y square, and then when you multiply it by exponential minus y square by 2, the whole thing goes as exponential y square by 2, and this would certainly go to infinity as y goes to infinity. Okay. And that is not a desirable case for any wave function, because the wave function should be finite, and it should be finite and continuous everywhere, because of the reason that your psi of, I am just writing it as x, we no longer have x as a variable, position variable, but in general this thing will always be true. And this tells you that for the square integrability of the wave function, this is called square integrability, because it is when you integrate the square of that, it should give you some finite number. And clearly, if the wave function goes to infinity as y goes to very large values, then the square integrability is going to be harmed, and that is not a sort of desirable situation. And if that is not a desirable situation, we fall back onto the other option that we have, that epsilon has some quantized values, and this quantization goes as 2n plus 1, which is like an odd integer, that is for any n including 0 here, and that is the subtle difference that I was referring to compared to the case of the particle in a box, which did not have n equal to 0 to be an allowed solution. And if this is true, that is when epsilon n becomes equal to 2n plus 1, that is an odd integer, f of y is a Hermite, becomes a polynomial in y, which is called as a Hermite polynomial of degree n. Okay. And it is a nice polynomial, and in fact, there is some physics that I want to discuss here. I have written, of course, in terms of nz and z. So, this hn z is what you see here. So, for n equal to 0, as I said, n equal to 0 is allowed, and so n equal to 1, it is equal to 2z, which means 2y if you write it in terms of y, and for n equal to 2, it is minus 2 plus 4z square or minus 2 plus 4y square, and so on. So, there are a few Hermite polynomials, values of the polynomials that are listed here. One important thing to note is that whenever n is even, the polynomial has even powers of z. That is, if you invert z to minus z or y to minus y, they remain invariant. That is, the Hermite polynomials do not change their sign. But for the odd ones, that is n equal to 1, 3, 5, etc., it involves odd powers of z, and which means that they would invert their sign, or they will change their sign if z goes to minus z. So, under this inversion operation, they change their sign, and that is precisely is meant by the inversion symmetry, and this inversion symmetry ensures that the entire linear vector space actually fragments into odd solutions or odd ends, and even solutions or even ends. And this is a special property when you have this right left symmetry, which is called as a parity or as the inversion symmetry. There are many other important relations about these recurrence, these Hermite polynomials. In fact, the Hermite polynomials, they can be, if you know n and n minus 1, then you can generate the n plus 1 and so on by this relation. They have generating functions, etc., that comes in mathematical physics. So, we will skip these special functions or the studies of the special functions from this course, because it is condensed in terms of its contents, and there are many things that need to be done. But you can read from Afghan or Krzyzczyk, any of these books will give you a nice introduction to all these special functions, including the Hermite polynomial that we are discussing here. So, what we have nicely got is that this epsilon becomes equal to 2n plus 1. If you look at this, the transformation, that is E equal to h cross omega by 2 epsilon. So, E becomes equal to h cross omega by 2 and then a 2n plus 1, and that tells you that this is equal to n plus half h cross omega, and that is a result that you must have seen. This is how the energy levels of the harmonic oscillator are quantized, and when n can take any value, n equal to 1, 2, 3 and so on, okay, including 0, and this n equal to 0 is called as a 0 point energy. So, the half h cross omega is a 0 point energy, which is not equal to 0. Okay. In the sense that that is greater than 0, so this is even the lowest energy state, the oscillator, they will have some finite energy which is equal to half h cross omega. So, what are the different eigenstates of this oscillator? The different eigenstates are, the ground state is say for example written as a constant into a Gaussian. This factor is known as a Gaussian exponential minus some alpha x square, the first excited state which is psi 1 of x, we have gone back from the y variable to the x variable, and this is the final form of the eigenstates that we are representing. So, it is a1 x, where a1 is some constant x exponential minus m omega by 2 h cross x square, and so on. So, you have so this is the basically the first Hermite polynomial, which is h1 x. Of course, you see there is a factor of 2 here, there is a 2z which should be 2x here. So, that 2 factor has been absorbed in this a1. Okay. And if you want how to get these a0s, a1s and a2s and so on. So, in general they would be written as an hn, and then there is alpha x, and then there is an exponential minus alpha square x square, where alpha is given by root over m omega by h cross. And how did we find out these values of a0 and a1? That is easy, because your psi 0 mod square dx minus infinity to plus infinity should be equal to 1. So, that tells you that a0 square, in principle I should write it as mod a0 square, because it can be complex, but here of course we have real these things, and we have exponential. Now, there are two alpha square x square, because there are two, there is a 2 factor, and there is there is a factor of 2 also here. So, let me write, forgetting this factor of 2, you can adjust this alpha, let me then call it as beta, so that you do not confuse it with the same alpha. So, beta is something that can be written in terms of alpha, and this is nothing but a Gaussian integral with a value to be, so exponential minus, let me just write it as beta. Beta x square minus infinity to plus infinity has a standard value which is equal to root over pi by beta, and then put it here and make that equal to 1, and you can get a0, which is how it is obtained as m omega by pi h cross whole to the power 1/4. Similarly, you can normalize the first excited eigenstate, which is psi 1 x, and by the similar prescription, and you can get this a1. So, in general, this psi n of x has a polynomial which is h n of alpha x and a Gaussian. So, there is a polynomial which has a name. Now, we know that it is called as a Hermite polynomial, which has a property that for n equal to even, it is an even polynomial in x, and for n equal to odd, it is an odd polynomial in x, which means that as x changes sign, x to minus x, whether the even will not change sign and the odd will pick up a negative sign. All right. So, so that is the solution for these harmonic oscillators. So, I will show you the picture, or rather a depiction of these eigenstates, different eigenstates there. So, what we said earlier, let me sort of remove this so that you can see it clearly. Now, since you know that how to do that integral, let me write that integral here. So, exponential minus beta x squared dx from minus infinity to plus infinity is equal to root over pi by beta. Okay. So, E is equal to, I can put an n here, because n means that there are different energy levels that are allowed for the oscillator to take, and they are in integer multiples of h cross omega by 2. So, the lowest one is h cross omega by 2, then it is 3 h cross omega by 2, 5 h cross omega by 2, and so on and so forth. So, these are ground state, first excited state, second excited state, and so on, okay, whose eigenfunctions are given by these polynomial convoluted with the the Gaussian, which means that for the ground state this polynomial has a value 1. So, it is purely the Gaussian, which so a Gaussian looks like this, and the first excited state, which is already written there, which is a1 x into exponential minus m omega by 2 h cross x square. So, the second one will have a value that is will have a value like this and so on. We will see that I probably did not draw it properly, but so this is the lowest one, and then this will also be like this and so on. Okay. They are shown as this. As you see, the lowest one is simply a Gaussian with an energy which is half h cross omega. The first one has a node here, this is what I was trying to show, with an energy which is which is 3 half h cross omega, not minus, it is 3 half h cross omega. And the second one has of course 2 nodes inside the well, which is 5 half h cross omega. Then there are 3 nodes, 4 nodes, and so on and so forth. So, these are different these quantum numbers. So, n is called as a quantum number because that precisely sort of distinguishes different states, including the ground state, and then of course, the first excited state and second excited state. And there is a picture that shows that this is how the wave function looks like. So, the wave function as opposed to the particle in a box which abruptly ends at the boundaries because it cannot go anywhere out. Here of course, the potential is finite, and the wave function actually has some extent in the classically forbidden region, which are these region that you see here and here and here and here and so on. So, they they are nice Gaussians. They do not end abruptly at the edge of the oscillator, but smoothly dies off to 0 as exponential minus some constant into alpha square. Okay. The next problem that we want to do is that the solution of the Schrodinger equation in 3D, and precisely what we will do is the hydrogen atom. Let me just go one slide back and just introduce a 2D harmonic oscillator. What do you think this would be? Would it have any special feature as opposed to what we have seen here? So, we will have say a particle is executing oscillation, simple harmonic oscillation in x axis along x axis, and it is also executing simple harmonic motion in along y axis. So, it is kind of making an oscillation in the x y plane with having displacements along both x and y direction. So, we will simply write the V x y is equal to half m omega square x square plus y square, and the entire thing that we have done in just 1D oscillator will replicate that to the for the 2D, and what we have is that we will have this psi nx ny, now no longer just a single quantum number, but there are 2 quantum numbers, and this will be like h n x alpha x and some h n y alpha y, and then of course, this exponential minus beta, let me write it as just keeping the notations there. So, it is alpha square x square. So, minus alpha square x square plus y square. So, you see that what we have done is that we have simply replicated the problem and have appropriately added or rather here multiplied the wave functions, and the energies will not be something any different. We will have these indices that need to be considered, and this will give you a nx plus half plus ny plus half and h cross omega. So, there will be a 0 point energy corresponding to each one of these. This will give us a nx plus ny plus 1 into h cross omega, and that tells you that there is something new that comes up. There will be suppose nx plus ny is equal to say 5, say. Okay. So, we are just talking about this 5 half h cross omega that you see, or now it will not be 5 half, but it will be like 6 h cross omega, because it is a 5 plus 1. Now, how can you make 5? You can make 5 by 0 5, you can make 1 4, you can make 2 3, you can make 3 2, you can make it 4 1, you can make it 5 0. all these choices of nx and ny will give you the same result as 5. So, which means that all these states are degenerate in energy, they have the same energy, but they would not correspond to the same eigenfunction. So, so the notion of degeneracy is very important in larger than one dimension, where the energy of the particle or the energy of the electron or energy of whatever you are considering will remain same for different values of their quantum numbers. However, their eigenfunctions are not identical, they are in fact they would be orthogonal to each other. So, each of these choices like nx equal to 0, ny equal to 5, it will be orthogonal to nx equal to 1 and y equal to 4 and so on and so forth. So, this degeneracy is an important thing, and this is going to be discussed even for the hydrogen atom. Okay. There is another thing that one can think about, that suppose this oscillator is charged, and so not only it has a mass, it has also a charge and I mean some charge, okay, so positive, negative, whatever. And suppose you place this, it executes a simple harmonic oscillation and you put it in an electric field. Okay. So, when you put it in an electric field, there is an additional potential that comes, which is equal to say QEX. We are not committing that what is the sign of Q, but any charge would do, and E is the electric field. So, let me change this symbol because E is also energy. So, E is the electric field, and so this electric field would sort of there is another potential energy that will come in, which is equal to P. It is like a P dot E, and P is equal to the dipole moment. So, the oscillator will develop a dipole moment, and because of the dipole moment it will have a potential. So, the total potential energy, so this is due to, let us call it a dipole potential. So, V is equal to half m omega square x square plus q E x. Now, the question is that whether you can solve this problem exactly, and it turns out that it is not a difficult problem to solve, you just have to complete the square. So, if you add and subtract some terms such that you can write this as some x plus x naught whole square, then it still looks like a harmonic oscillator with these energies given by n plus half h cross omega, excepting that now the oscillator will no longer execute oscillation about x equal to 0, but that point, the equilibrium point, now would be shifted to some x naught. Okay. So, that is the only thing that you have a change there, but other than that the problem remains identical. So, even if you have a charged oscillator in an electric field, you can still continue treating it as sort of uncharged one, excepting that the equilibrium point shifts. So, let us go on to Schrodinger equation in 3D and we will again get what we have seen, the degeneracy and so on. This problem is significantly complicated as compared to the 1D problem because of one, it is in 3D, second it is in there are r theta phi coordinate system or the spherical polar coordinate systems that needs to be considered, and why it is important to consider a spherical polar coordinate system, why can't we do with Cartesian coordinate system. And the reason is simple, that we have to abide by the symmetries of the problem. If you have a spherical symmetry, because the hydrogen atom is just like an atom, the simplest atom, this is what is being said here. So, it has a nucleus at the center, which is what we have learned from the Rutherford scattering. So, it is the simplest of all atoms and made up of positively charged proton, and with the rest mass equal to this is the proton mass, and the electron has a mass which is like 3 orders of magnitude less. And so, it is the only atom which has got 2 particles, and this makes this analytic solution of both the classical as well as the quantum mechanical dynamics of hydrogen atom to be easy and tractable. So all other atoms are composed of the nucleus and more than one electron, and we still can handle, say for example, helium atom in some either exactly or doing some variational calculations, which is what we will see later. So, in any case, the Schrodinger equation for this case looks like this Laplacian of psi, which is del square psi plus 2 m naught by h cross square e minus v of psi, and so on. And this m naught is same as mu. You would see that most often it is written as mu, which is the effective mass, which is written as the mass of the proton multiplied by the mass of the electron divided by their total mass. So, that is called as a reduced mass or effective mass, whichever you want to call it. And this r is nothing but equal to r theta phi, okay. And r is the radial variable, theta is the angular variable or the polar variable, and phi is the azimuthal variable. And what is V of r here? V of r is some E square, which is a charge. You can, in this particular case, it is simply E square because proton has a charge E and electron has a charge minus E. So, it is minus E square by 4 pi epsilon 0 r, and this r that you see in the denominator is a distance between the proton and the electron. So, this is the form of the Laplacian, that is a del square operator in a spherical polar coordinate system, that is the r part, and the theta phi parts are combined. And in fact, a lot of books or a lot of texts that you would come across, they do the angular momentum problem ahead of the hydrogen atom. We took a different stance because we sort of thought of solving Schrodinger equation for different kind of potential, but nevertheless why angular momentum is done ahead of this is that the thing that you see in the bracket is the angular momentum or the square of the angular momentum operator apart from some constant. Okay. So, first if you solve this and know the eigenstates of the angular momentum operator, then of course it becomes easier to introduce. Then we really need to know solve for the r part or the radial part, and because the theta phi part is already solved, and these have a solution which are known as the YLM functions, which are functions of theta and phi. They are called as spherical harmonics. Once again, we will not solve elaborately, but this r, theta and phi, they can get decoupled, and you can write down the solution in terms of r of r, theta of theta, and phi of phi. And this is the radial equation, and this is the theta equation, and the phi equation is very simple, which gives a solution which is like exponential plus minus I m phi, while the other two are a little more complicated. These are these PL functions or these Legendre polynomials. They are they come out as solutions of this, and for the theta part, and what we get is the log-ware polynomials for the r part. So, now the r part is in terms of the log-ware polynomials. We do not go into details of the solution, and the theta and the phi parts, they correspond to the put together, they correspond to this YLM or the spherical harmonics, and we just have to multiply the log-ware polynomials with the spherical harmonics in order to get the different bound state eigenfunctions for the problem. And again, we have to solve by solving this Schrodinger equation that you see there, or rather solving all three of them, we should be able to construct the eigenfunctions and get the energy eigenstates. And of course, we would get the bound states with negative energies, for the reason that the electron is really bound to the nucleus or to the proton, because otherwise it will just fly away, and that does not happen because there is a very large binding energy between the electron and the proton, and that is what we want to find out. So, as I said that this is the radial solution and the YLM solutions. At times the YLMs are written as this, and in some texts it is written as YL with a but they are identical. Okay. So, this is M, and as I said that they are functions of theta and phi, and this RNL is simply a function of R, the radial variable. This R is a scalar variable which goes from 0 to infinity. Okay. Theta goes from 0 to pi and phi goes from 0 to 2 pi. So, we do not go into the details, but want to reflect upon the first few eigenfunctions of this. So, this eigenfunction, the ground state, this is called as a ground state. And the ground state eigenfunction looks like 1 by root over pi a0 cube exponential minus r over a0, where a0 is called as a Bohr radius. Okay. So, this falls off, unlike the harmonic oscillator, it falls off as exponential fall off. We will show the pictures, the schematically we will show these wave functions, and we will also talk about these quantum numbers. So, n is a quantum number, L is a quantum number, M is a quantum number, and these three quantum numbers, they actually denote the energies of the system or the degeneracies. Very importantly, they would define the degeneracies and so on. So, these N, L, M that you see here are the three quantum numbers. They are called as principal quantum number for L. L is called as azimuthal quantum number, and M is called as a magnetic quantum number. And because of this, there are n can take values from 1, 2, 3, etc. integer values. L will take values from 0 to n minus 1, and M can take values minus L to plus L. So, these 2 L plus 1 values, and we will see that how these different interlinked sort of dependencies, they would give rise to the degeneracy. So, these first few things, eigenfunctions, one is this is simply exponential minus r by a0 with some normalization, which is 1 by root over pi a naught cube, and then we have again polynomial multiplied by these exponential function. So, this is 2 0 0, and 0 zeros, that is whenever L equal to 0 and M equal to 0, they do not have any theta or phi dependence. They only come when you have the L or M or both of them to be finite. So, you see that psi 2 1 0. So, this is the ground state, and all these are excited states. In fact, you will see that these three, they are a degenerate first excited state, which means that they have the same energy. However, they correspond to three different distinct eigenfunctions, and which all are orthogonal to each other. They kind of are orthonormal, sort of eigenstates. And then there is a psi 3 0 0 that is shown there. And so, these are different eigenstates or the bound states of the system. And what about the the bound state energy spectrum? The bound state energy spectrum is given by this minus m0 e to the power 4. We were writing it E0, but it is just the electronic charge, and then 8 epsilon 0 square h square by 1 by n square, and there is nothing but equal to minus 13.6 by n square, and n is called as a principal quantum number. Okay. So, that tells you that the energy level of a hydrogen atom is minus 13.6 by n square electron volt. So, if you give 13.6 electron volt, when the electron is in the ground state of the hydrogen atom, it will escape. That means, the hydrogen atom will lose that electron and will become an ion. So, that is called as the ionization energy of hydrogen. So, let me show the pictorially how the radial wave functions look like. So, these are S states and so on. So, you see the S state is this is the R10 state, and this is the R20 state, and this is the R30 state, and these are the P states, which are again this is like R11 state, and so this one, and then this is R21 states, and this is R31 states, and these nomenclature, and it's plotted, this is the radial part, that is RNL, multiplied by R is plotted as a function of R, okay, in terms of the bore radius, which you can call as A0. So, it is R over A0 and so on. Okay, so, S and P states, so S states correspond to L equal to 0, okay, and these P states correspond to L equal to 1. So, the S and P states are shown. Similarly, you can plot the D states and F states and so on, which are corresponding to L equal to 2 and L equal to 3 and other higher values. So, it is important to look at the probability density, you know, how the probability density and the wave function, they vary. So, this for the 1S state, it sort of quickly falls off, it is plotted in, you know, kind of angstrom. The 2S has, it goes down, and then it sort of, you know, picks up and becomes mildly positive at large values of R, almost 0, and then you have a 3S and so on and so forth. So, you see that the probability density behaves like this for the 1S state, and then it has a 0 in between for the 2S state, and it has 2 zeros in between for the 3S states and so on. This tells you that as you go to larger and larger the quantum number, the principal quantum number, or you know, associated with R, which is the principal quantum number, and these S values say that its L value is equal to 0. There are more fluctuations, you know, as you go to larger and larger values of N. So, we are really talking about RNL square, and this is R as a function of, you know, R in angstrom. This is not you know, scaled by the bore radius, whereas in the earlier figure it was scaled by the bore radius. Similarly, for the P states and the D states, they look like this. So, the 2P state, you have a peaked you know, density close to say R equal to say 3 angstrom or something, and for the 3D it is peaking at about 5 angstrom and so on, and this is how the P state and the D states, 3D states look like. So, this first one, as I said, correspond to the value of N, and the second one will correspond to the value of L. So, so this means N equal to 2 and L equal to 1. Similarly, this is N equal to 3 and L equal to 2. Okay. So, that is the depiction of the wave function and the probability, and if you plot the angular orbitals, so this is the S wave, and then there are 3 P waves which look like Dumble, Px, Py, Pz, and then there are 5 D orbitals which look like these blobs along the axis and so on. And there are 5 of them called dxy, dyz, xz, dx square minus y square, and dz square. These are the 5 orbitals. So, this is you know, L equal to 2, this is L equal to 1, this is L equal to 0 and so on. So, the multiplicity is 2L plus 1, and that is why you get 5 for this, you get 3 for L equal to 1 and so on. Okay. So, the S orbital is spherically symmetric, that is the ground state is spherically symmetric for the theta and phi dependent. So, finally, you know, coming to the quantum numbers and degeneracies, we have told this that N corresponds to the principal quantum number, it can take values 1, 2, 3, etc. L is called as the azimuthal quantum number, it can take values 0 to n minus 1. M corresponds to the magnetic quantum number, it takes values minus L to plus L. So, if you need to calculate the degeneracy, you need to actually have the degeneracy of M values, and these M values can take 2L plus 1 values, and if you try to calculate this, this becomes equal to, so 2 L equal to 0 to n minus 1 L plus 0 to n minus 1 1. Now, this can be, it's like so 2 into, so it is n into n plus 1 by 2 when you are summing numbers from 1 to n, but this from 0 to n minus 1, it will be n minus 1 into n by 2, those many values, and then you are just simply summing up 1 n times. So, that gives you n. So, this is the 2 will cancel and you have a n square minus n plus n. So, this becomes equal to, simply this n will cancel, it is a n square fold degenerate. So, each of the states of hydrogen atom are n square fold degenerate. Ground state, which corresponds to n equal to 1, is non-degenerate, n equal to 2 is 4 fold degenerate, n equal to 3 is 9 fold degenerate. But here of course, we have not taken into account the spin degeneracy. So, if you take into account the spin degeneracy, so including the spin degeneracy. So, this is the degenerate states. So, this ground state is non-degenerate, but this degeneracy that we are now talking about is not 3, this is equal to 4 and this is equal to 9 and so on and so forth. So, there are there are 9 states which are degenerate. Then as you go there up in larger, for larger values of n, you get these degeneracies to increase as n square. So, including the spin degeneracy, we have this as 2 n square. Because this spin degeneracy brings in a 2s plus 1 factor, and because this electron has spin half, so this 2 factor of 2 comes out. So, this becomes 2 n square. So, in fact, this degeneracy for the ground state is it's again non-degenerate, but then this is like 8 fold degenerate and this is like 18 fold degenerate, and the next one would be 32 fold degenerate and so on and so forth. Okay. Okay, so we are there with this angular momentum. So, this is the angular momentum is defined as r cross p. So, this is written as x, it means it is r cross p, and so it is a cross product, it is a moment of the linear momentum. And now with this the Hamiltonian that we have for the hydrogen atom that commutes with all of these 3. But the problem is that each of these angular momentum components or the operators corresponding to them, they do not commute, and because they do not commute, you cannot use all of them as or rather you cannot find the eigenstates of H to be the same with all of them. So, rather we choose L square, which the H commutes with L square, that is the Hamiltonian for the hydrogen atom commutes with the angular momentum square, and it also commutes with Lz, and L square commutes with Lz. Of course, L square commutes with Lx as well, but that is not so important. So, we take these two as the basis for constructing the eigenstates, and this gives you this YLM functions, which are functions of theta and phi. Okay. So, this exactly this is what we said earlier, that this is a radial part, and we have written this radial wave function as UE, because E corresponds to the this principal quantum number, because energy is quantized as this minus 13.6 by n square, and this is again the wave function that is written there. That is not important. What is important for us is that the L square acting on YLM gives you L into L plus 1 H cross square and returns you this YLM function. So, YLM functions or the spherical harmonics are nothing but they are eigenstates of the L square and the Lz operator, and we have chosen it that way. We need two operators as preferred ones. So, we could have chosen L square and Lx or L square and Ly, but then the simultaneous eigenstates of L square and Lz will have to be, or Lx will have to be determined. This is much easier, because Lz acting on YLM it gives you MH cross into YLM theta phi. You can also use the raising and the lowering operators, and which finally gives you these, of course, these raising and the lowering operators, which are Lx plus ILy or Lx minus ILy, which are L plus and L minus respectively. For them, of course, because Lx does not commute with Lz, these are not the eigenfunctions. So, they actually raise the magnetic quantum number by 1 unit, or they lower it by 1 unit, depending on whether you are talking about the raising operator for the angular momentum and the lowering operator for the angular momentum. In fact, we we have introduced the angular momentum, but we wish to do a little more and wish to talk about specifically for the spin angular momentum, which has a different name for these spin half particles. These are called as the Pauli spin matrices, and we will see some of the properties of Pauli spin matrices. But that pretty much finishes one important task in quantum mechanics, that is solution of Schrodinger equation in a variety of potentials, including some constant potential, potential discontinuities, potential wells, delta function potential, harmonic oscillator, and finally the hydrogen atom, which is a 3D problem solved in the spherical polar coordinates. In each one of those cases, we have calculated the energy eigenstates and the eigenfunctions corresponding to those states. That makes the solution complete. Of course, you can do many things with the eigenstates. Eigenstates are you can calculate by taking a mod square of that. You can calculate the probability, you can calculate the probability current density, etc., and satisfy yourself that the equation of continuity for each one of those cases is satisfied. And we will see a little more on that before we go on to perturbation theory. We will stop here for today. Thank you.